Share screen. Very well. Okay, we're ready.
Adelante.
Okay, fantastico. Fantastic. So I am Pablo. This is Frederi. You're about to watch a very short, condensed version of the introduction to Bayesian statistics video we just recorded. That is around 45 minutes. So this one we're going to try to streamline it. 10 minutes, you see what it's about, and then if you're interested in more details, you can go to the longer version.
The long version's fun.
The long version is really fun. We had so much fun. This is the outline that I'm not going to read to not waste time. The main point that we want to make is that there is a lot that you can learn from data if you use statistics. Some of the examples that I would put is the Higgs boson, the relationship between smoke and lung cancer, and some applications to nuclear physics, and in this other case, COVID responses. And we put an example of the German tank problem, which is a fantastic problem if you haven't heard about. All of these things, from a Bayesian point of view, hinges on Bayes statistics, which makes sense because it's Bayesian. And the main idea is that you want to model all the variables in your system whenever you're trying to, you have, for example, some data and you're trying to fit a model, and you try to understand how that relationship works through the parameters of your model.
Yeah, so in this case, we have y is response and x is the input variable. So it's an input-output system. The model is the function f, nonlinear here, the red curve. It depends on a parameter. In Bayesian statistics, we think of the parameter as having the parameters has some uncertainty to it. If we have some data, we can figure out what the parameter is with some uncertainty, and then the uncertainty, how do we model that using Bayesian statistics? We think of it as being a random variable, and there's a relation here on the right-hand side which relates the as Tio Pablo is going to tell us in a minute, the randomness in that random variable alpha. The capital P represents probability, the capital Y represents the data that we have, and the uncertainty modeling on the relationship between the data. So please go ahead.
And we have not much time, so the main idea is that we want a posterior distribution, that probability distribution on the parameters given the data we observe, and we do that through Bayes theorem, which relates that through the likelihood, which is how we think the data came to be, and the prior, which is any prior information we know about the data or the parameter. So in this case, for example, you could say my parameters are positive. You could model your likelihood on how the data came to be through what in usual physics is known as a chi-square function. And we went in all detail saying that this is a specific type of modeling. You're making a lot of assumptions about your data and the structure of your model, and most of the times this will not hold true. So you need to be careful. This will most of the time end up in underrepresenting uncertainties. In particular, your data doesn't have to be Gaussian. Your data doesn't have to be uncorrelated. Any comment you want to make on this?
Well, for this slide, yeah, I mean that part's fine. Like there's this P of y, which is in a gray box in the denominator there on the right-hand side of the equation. You can kind of ignore that. What's really extraordinary about the Bayesian formulation is that the probability distribution of what we're looking for, which is the alpha, given what we know, which is the data and the model that we have about the data, is proportional to the product of what we believe about alpha to begin with, without any information from capital Y, without any data. What we believe in, you multiply the probability of what we believe about alpha times the chance of observing what it is that we have observed, given our model and given some specific values for alpha. You multiply those two things together, and that gives you the chance that alpha is what actually is going on, given the data that we have. And that's an extraordinarily simple formulation. That's the key behind Bayes.
And made by Thomas Bayes.
Thomas Bayes.
If you want to know more about, you can watch the other video. So this is how a typical day of a Bayesian statistician looks like. You start talking with your experimental and your theoretical friends to trying to explain some, in this case, nuclear physics data, for example, reactions. And in those conversations, part of it is going to be around the prior, how we're going to quantify the previous knowledge we have. For example, one of the parameters in this reaction model has to do with the size of the nucleus. So your theoretical friends might tell you, oh, we think the nucleus is between, the radius of the nucleus is between here and here. Part of the discussion is going to go on the likelihood, trying to understand how these data came to be. And that is a fantastic conversation to have directly with the people that were involved in the experiment. And then they can tell you, you know what, actually, this point that is around 2.3, we don't believe it much. We think something weird happened with our detectors. So at the level of our statistical modeling, we're going to treat that point separately, for example, and that is completely valid. That is putting information in a mathematical formulation to help us. Part of the discussion could be, are there any other models that we're going to take to explain the data? And some theory friends might say no, and then some other theory friends might disagree and say, yes, of course, I have a model that also explains the data. So there are ways, and we're going to talk about this in the Bandcamp and at ISNET in general, but there are ways where you can combine these models and do Bayesian model mixing, for example. And one final comment on all of these, okay, perfect. One final comment on all of these is that many of these Bayesian calculations require thousands or millions of evaluations of your theoretical models for different values of the parameters, and that is usually computationally very expensive. And there is a lot of research, and we will discuss that in Bandcamp as well, on the building of emulators. And some people, like myself and my friends Kyle and Edgar, we are very much diving into that and having a lot of fun with it. The final product of all of this process is to have a posterior distribution that looks like this, where you can say, these are my probabilities distribution for my parameters. I can talk about correlations, and then I can make predictions with uncertainty band, in this case, or credibility intervals, for both of our models. And after that, we have 3.5 minutes to go through the code. Once again, if you want to know more details about all of this, I suggest that you watch the longer video. But in this one, we're just going to show quickly a code we wrote to make some examples on how this might go through. So in this case, we imagine that we have some data with some errors, and we're showing the true function that generated this data, but of course, most of the time you don't have access to that true function. And what this code does is guiding you through the process of creating a likelihood model, creating your prior, given the previous knowledge that you may have about this data, and doing the sampling.
You're going to share this code, right?
Of course, we're going to share this code, so you can go through it and in your own time. So the first case that we showing here is
what you meant to say is at your leisure.
At your leisure.
Yeah, you can go through this code at your leisure.
Perfect. So the first case is where we actually know the errors, and the errors are correct, the picture that I showed before. And after you run all the Monte Carlo samplings, which is how to get posterior distribution from your parameters, this is the uncertainty quantification plot that you have with your 95 credible interval for your predictions. And everybody's happy, everything works perfectly well. And this is a final posterior distribution you get from on your parameters.
This is a representation of the posterior. These are your credible bands in 2 dimensions here for these two parameters, alpha 1 and alpha 2.
And this red point that is showing both the value here and the value here is showing the slope and the value at 0 of the true function, because we just made it up that's what we were after in estimating. The second case that we present is what happens if one of my points is an outlier. This point right here, what happened if the uncertainty was underreported?
Oh, this is a real problem in nuclear physics and in other areas. People underreport uncertainty all the time.
And now our model is super biased toward that point.
So that's that tiny little bit of uncertainty that was reported, whereas they probably should have reported something much bigger.
So now if you run the entire thing, well, the value of your estimation of the slope and the value at 0, actually you miss it. And that is the point. The point is because the uncertainty was under.
I mean, this is a good example. There's only 7 data points in this problem. One of those data points was severely underreporting uncertainty. It has a huge influence on your answer.
Exactly.
But if you have 100 data points and 12 of them have this bad feature, then you're going to get the same issue.
Or worse.
Or worse.
The third case is what happens if now everything is completely well reported, but now you have a new data point. And the true function that was generating this, we thought it was a linear function, a straight line, but actually it was a sine function. So now we observe this new point and we realize our model is not as good as we thought. What are we going to do? And the idea is that these procedures allows you to test, well, what if I try with a model that has more parameters?
Evidently,
that explains
we're never going to do well in this particular issue here because the model that we're using is so far from the actual function. So there's no way that we could win here with only one data point.
So what you can do is you can increase your model to consider a quadratic term. And once you do that, things start agreeing more with the data. You have some uncertainty bands that actually
even with just that one data point, if we're smart enough to use a quadratic function, which the sine function does look quadratic within this particular area, it works much better.
And finally, you end up having posterior distribution for the 3 parameters of your model, and you can infer correlations between them. So now we have 37 seconds for the last part. The final closing comments. The first one relates to the Bandcamp that we're going to have in ISNET. This is the band map, the type of tools that we are developing to help people achieve many of these tasks. And on May 22, Monday, we're going to go through many of these tools that we're developing at the band collaboration. So please come and stay tuned if you're interested in that. And the final part is a challenging problem for all of you. Basically, go through the code, and in the parting where we're using the errors for the points, erase the error and try to estimate those errors by your own hand.
And if that's too hard, you can just pretend like all the errors are proportional to a single parameter and try to estimate that single parameter, assuming it's not known.
And we have the alarm. So we're done. Thank you, everybody. See you there, and check out the longer version if you want to know more details.